Superconductivity, an extremely cool but unexpected phenomena used for levitating objects. It's used for MRI scanners, and it might just one day revolutionize completely how we transport energy. In this video I will tell you the physics behind it and a little bit of the history as well. Superconductivity was discovered in 1911 by Heike Kamerlingh on Ace. It was just made possible to liquefy helium, which produced extremely cold temperatures. Here, on this temperature scale, we have Celsius, and at 0, of course, water freezes, and at 100 degrees Celsius, water boils. At negative 273, we have the absolute zero, and a little warmer is the liquid helium, but it's still extremely cold. To put things into perspective, here is liquid nitrogen. It's negative 195 degrees Celsius. Let's switch the units to Kelvin. Of course, we just set the absolute zero at the 0 point on this scale here, so you can see the temperatures. Now for my American friends, here's the same scale but with the Fahrenheit instead, just so you can get a feeling of the temperatures. Now we can reach temperatures down to 3 Kelvin. We can use that to take a look at circuits. So here we have a battery and we have a cable connecting it. That will of course induce a flow of electrons. If we zoom in on the cable, of course the cable is a conductor, so we will see the metallic lattice, and we will see that the electrons are loosely bound to the nucleus such that they will move easily when they feel a potential. Now compared to that with an insulator, their electrons are strongly bound to the nucleus, so it won't conduct unless we give it enough energy. Just as you know from thunder, you wouldn't say atmospheric air is a really good conductor, but there's just too much energy in the system, so the air will conduct indeed. Anyways, if you go back and take a look at the cable again, of course this was a bit an idealized model because we have temperature in the system. This means that we will have random movements, and the random movement will cause particles to collide and lose energy into thermal energy. So a higher temperature will cause more energy loss and will cause, of course, bigger resistance in the cable. Let's graph that. On the x-axis we have temperature, on the y-axis we have resistance, and as temperature increases, so does the resistance. Actually, at the time, it wasn't known what would happen if we drop the temperature further. Would the resistance drop to 0 as the temperature reaches 0? Or would it perhaps reach a constant resistance? Or maybe even too cold will cause even more resistance? That wasn't known at the time, but now with the extremely cold liquid helium, we can just take our system, take a look at a fraction of the cable, apply extremely cold liquid helium to it, and measure what happens to the resistance in that area. Are you ready? Because for some materials, this happened. After being cooled down under some specific temperature called the critical temperature, there is absolutely no resistance at all.
Why?
Okay, we'll get to the why in a second. I just want to point out that we know there is no resistance at all in the conductor. You know, there might just be an extremely small resistance, but there is none. We know this because we can create a ring out of superconductive material, let a current run, leave the system for years and come back later. This has been done, but there is no measurable loss in the intensity of the current. Also, I want to point out that superconductivity is not really a rare phenomenon. Here on this periodic table I marked all the superconductive materials. You can see it's actually quite common to be superconductive. Okay, so now we will get to the why there's no resistance. Let's come back to our conductor and observe just one electron and assume the conductor has been cooled down by helium, so the thermal vibrations are negligible. As the electron is being pulled to the positive side of the battery, it flies in between atoms of the lattice. These atoms are positively charged because they have lost their electron to the conduction. This means that the electron will cause a slight attraction of the atom, since it's negatively charged and the atoms are positively charged. If you have a positive atoms clumped together in a local disturbance, they are a bit more positive. Now, a new electron flying in will be attracted to this local disturbance, because it is slightly more positive charged. You would probably expect, since like charges repel, these two negative electrons should repel each other. But they don't, because in reality many more atoms in the lattice is actually a part of this disturbance. And the attraction happens over hundreds to thousands of atoms. The attraction causes these two electrons to go together and bind to what's called a Cooper pair. But this bond is extremely weak, and even thermal vibration will break it. That's why we needed the liquid helium. When two electrons go into a Cooper pair, something interesting happens.
Protons, neutrons and electrons are usually what's called a fermion particle. There's another type of particle called the boson. A photon is a boson. I'm not going into details about this, but being a fermion, like the electron, means that no two particles can be in the same state. That's why we see atoms like this. We have fermions, electrons, orbiting the nucleus. If they were bosons instead, they could all go into the same state. So they would all clump into the ground state and no chemical reaction could occur. But bosons can be in the same state, and that's important for superconductivity. Because when two electrons go into a Cooper pair, they are still fermions, but they act together as a boson. That means all the Cooper pairs clump into the lowest energy level, and they will all be in the same state, because they are bosons now and not fermions anymore. Now they can behave as one big group of particles in the same state. Because the Cooper pairs are bounded over a big distance, more Cooper pairs become overlapped. This new big overlap becomes entangled and now behave as a large network of interactions. This network of interaction will be attracted to the battery's plus pole and therefore conduct. The collective behavior of all the electrons in the network and in the solid prevents any further collision with the lattice. If it were to collide with an atom, the network can just recombine into new Cooper pairs. To have resistance, the whole network will have to collide with the lattice, and that's just too uncertain to happen, so there is none. Another way to think of it is the current has to be resistanceless because you can't take any energy from a system that's already in its ground state, which these bosons are. So superconductivity is just a strange quantum dance of Cooper pairs, electrons and vibration in the lattice. There is much more to a superconductor than just zero resistance. Let's first take a look at the magnetic properties. If we put a normal magnet here, the magnetic fields are often drawn like this. They represent the direction and the strength of the magnetic field. So if we have other magnets, they would certainly be affected by it and would align it to this field. If we have normal matter, like this little cylinder here, and we put it next to a magnet, the magnetic field will just pass right through it, like nothing happened. But if we replace the cylinder with a superconductive cylinder, the cylinder will just repel the magnetic field. It will not have any magnetic field inside of it. This happens because the electrons inside the superconductor create small vortices that repels the magnetic field. Kind of like really small electron coils. Now we are actually ready to create really fast levitating magnetic superconductive trains. Because if we have a magnet up here, you can see the magnetic fields, and we have a superconductor down below, the superconductor will not have the magnetic fields inside of it, so this will not happen. The superconductor repels the magnetic fields, and therefore the magnet levitates. There's two types of superconductor, type 1 and type 2. What we talked about until now is all governed by a type 1 superconductor. Sadly, we don't know how a type 2 superconductor works, but that's really a shame because type 2 superconductors works on higher temperatures, and we are really interested in knowing that, because if we knew, we could put up a lot of solar cells without any loss of intensity and therefore solve the energy crisis. One day, perhaps. Thank you.